Yep. Welcome everyone. So this problem today is a pretty tricky one that uses the sequential property of density. So the density means like whenever a subset is dense, that means what? That if you take any point from the parent set, then you can always construct a sequence from that subset that will converge to that parent set's elements, right? So here the question is something like that. So it gives, first of all, it gives you a subset of 0 comma infinity in R, the set of all x that can be expressed as sum of elements of A is dense in 0 comma infinity. So that is something that we have to prove. So first of all, there are some of the remarks that we want to make, and then it will be clear. So let's take the subset that needs to be proved, as dense is let's say some x naught, capital X naught. Okay, so what we have to prove is that, so what is this? So this capital X naught is collection of all such elements. So as you can see that it is the collection of all such elements in 0 comma infinity that can be expressed as a sum of the elements, right? So x belongs to 0 comma infinity such that x can be written as sum of the elements of A. Okay, so let's just call it some summation over AIs. AIs belongs to A. So this is the set X naught. So this is something that we have to prove if it is dense or not. So if X naught is not dense in 0 comma infinity, this implies there exists a small x naught in 0 comma infinity which cannot be approximated by elements of x naught. So approximated means that there exists this x naught in whose epsilon neighborhood there does not exist any element of capital X naught. So this is what not dense means, that you will always find such an epsilon. Okay, so this is the first step. So you need to kind of understand what set you are trying to prove as a dense set. Okay, so now the second thing that you need to understand is that let a1 a2 be an interval in R positive. Okay, so suppose it's an interval in the positive section of a real line. So now if, let's just say, the value of y belongs to the R positive, that is the positive section of real number. If y is less than a2 minus a1, then a1 comma a2 contains n into y for some in natural number. So this is one of the very crucial observations that you have to make here. So if you take any interval and if you take a positive real number which is less than the size of that interval, then there exists a natural number n such that n into y will be inside that interval. Okay, so how do you say this? So you have y less than a2 minus a1, right? So that means what? That means you have this, that a2 minus y, this is greater than a1, and of course it is less than a2 because everything is positive. Y, a1, a2, everything is in positive real numbers, right? So if you have this, then what do you have? So then you have a2 greater than a2 by y minus 1 into y, that is greater than a1. So as you can see that if a2 by y is a natural number, it belongs to n, then you are done, right? So if a2 itself becomes y, then I mean, like, then that is a case that we are not considering, right? Because we are considering y, the value of y to be less than a2 minus a1. So like, if let's just say if a2 is equals to y, then a1 a2 becomes something different entirely. So we are not considering that case. So what we are considering here is if a2 by y belongs to n, then you are done, right? Because then this is your choice of n. But if not, so if a2 mod y doesn't belongs to n, then choose the floor function. So if you choose the floor function, then this floor of a2 by y minus 1, this will be your, this will be the number that is in n, and this is the number that you will choose as your n. So that means what? That provided any interval, if there exists an y such that y is less than a2 minus a1 always, then you can find a natural number such that n into y falls inside the interval. Okay, so now if these two things are done, what you can actually do is, so now let us get back to our hypothesis that if it is not dense, then there exists an epsilon such that you have a completely disjoint intersection with the set x naught, right? So what is x naught? It is the collection of x that can be written as sum of the elements of ai's. So far we have not used that 0 is a limit point of a. Now this is something that we are going to use. So if 0 is a limit point of a, then there exists a sequence yn in a that converges to 0, right? That is the basic definition of a limit point. So this implies for every epsilon, I mean, this is a limiting argument, right? So for every epsilon, there exists a delta such that all that limiting argument follows. So what that actually mean? It actually means that this is there. So there exists an y such that for a chosen epsilon, this occurs because of the existence of limit points. So this y is nothing but one of the elements in this sequence. So what does it mean to have a limit point? A limit point means in the neighborhood of 0, apart from finitely many, all the other elements will fall of the sequence. So from that, I have just taken one y. Now let us consider this set x1. So if I take this set x1 as n into y, n belongs to natural number. So as you can see that this y, it is in A. Okay, so y is in A. So x1 is practically nothing but elements of y, 2y, 3y, and so on and so forth. What is your x naught? X naught is the collection of x in 0 comma infinity that can be written as sum of elements of A. That means what? That means this x1 is practically a subset of x naught. Okay, got it? So as you can see that this y is chosen in such a way that it is always less than epsilon. So this implies, so from here we get that y is always less than 2 epsilon. All right. Now, if you take this x naught minus epsilon comma x naught plus epsilon, the neighborhood that we first started with, that x naught is not dense, hence there exists an x naught such that this entire thing occurs. Okay, but now this neighborhood, what is the distance of this neighborhood? The distance of this neighborhood is 2 epsilon distance, because x naught plus epsilon minus x naught minus epsilon is 2 epsilon, correct? So the moment you have 2 epsilon, what happens is that you now have an element in A which is less than the distance of this interval. So by this proposition, so let's say this proposition, we find, so now by proposition, we get that there exists some y prime in x1 that lies in x naught minus epsilon comma x naught plus epsilon. Okay, because that is what the proposition suggests. The proposition suggests that if you have an interval in the positive section of the real line, if the y is less than the distance between the interval, then for some n in natural number, n into y has to lie there. So here the distance is 2 epsilon. So that is the reason that, and if you look at the set of x1, this is practically collection of all like natural number multiplied to y for a fixed y. So, and that fixed y is also less than epsilon. So now you have this. So this implies that x naught minus epsilon comma x naught plus epsilon intersected with x1 is not equals to 5, and since x1 is a set theoretic subset of x naught, then x naught minus epsilon comma x naught plus epsilon intersected with x naught is also not equals to 5. That means x naught is indeed a dense set, because we have actually proven the statement via contradiction. So this statement is indeed true. Okay, that's it for today. Thanks for joining. We will meet with another problem from TIFR next time.